The illusion of understanding gravity feels obvious. Drop a stone and it falls. Throw a ball and it curves back to Earth. Stand still and the planet holds you in place. Because gravity works so reliably, almost everyone believes they understand it. Richard Feynman warned that this confidence itself is the mistake. We are taught that gravity is a force, that mass pulls on mass, that arrows point inward and equations tell the story. But calling gravity a force is not an explanation, it is a label. It replaces curiosity with comfort. Physics, as Feynman insisted, does not explain nature in the emotional sense people want. It describes patterns in what nature does. Newton's law of gravity does not tell us why apples fall, it tells us how they fall. When we say objects fall because gravity pulls them, we have explained nothing. We have merely renamed the mystery, just as saying opium causes sleep. Because of a dormitive virtue says nothing meaningful, this problem becomes sharper when we ask how gravity works at a distance. The Earth influences the moon without touching it, without a medium, without any visible mechanism. Newton himself found this disturbing. Action at a distance violated common sense, and Feynman emphasized this unease because it reveals how deeply gravity resists mechanical intuition. We like pushes and pulls because they resemble everyday experience, but gravity refuses to behave like that. Einstein is often presented as the one who solved this confusion, yet Feynman rejected that framing. Einstein replaced one mystery with a deeper one. Gravity, Einstein said, is not a force at all. Mass curves spacetime, and objects move along that curvature. The famous rubber sheet analogy tries to make this intuitive, but it cheats by using gravity to explain gravity. It provides a picture that feels satisfying and then shuts down thought. The real clue, Feynman argued, lies in free fall. If gravity were a force pulling you downward, you should feel it while falling, but you do not. In a falling elevator or an orbiting spacecraft, you feel weightless even though gravity is still present. What you feel when standing on Earth is not gravity, but the floor pushing up on you, preventing your natural motion. Weight is not gravity, weight is resistance. From Einstein's perspective, falling is not forced motion at all. It is the most natural motion possible. The Earth is what interrupts it. The first great misunderstanding about gravity is believing that it is something actively pulling objects downward, when in reality what feels like gravity is the world preventing free fall. Motion without forcing. Once gravity is seen through the lens of motion, it becomes even stranger. Ordinary forces require constant pushing to maintain motion against resistance. Gravity does not. The moon keeps moving without being pushed forward, endlessly falling while never landing. Feynman loved the image of the sideways falling cannonball because it captures this perfectly fast enough and the ground curves away beneath it. An orbit is not balanced, it is perpetual missing. Gravity does not hold the moon up, it allows it to fall endlessly. Energy deepens the mystery. Falling objects do not lose energy, they convert potential energy into kinetic energy while conserving the total. Gravity provides no fuel and consumes none. It rearranges energy rather than creating it. Another crucial clue appears when we observe that heavy and light objects fall at the same rate. If gravity were a normal force, increased mass should mean faster falling. Instead, the increased gravitational pull is exactly canceled by increased resistance to acceleration. This perfect cancellation is not approximate, it is exact, and it drove Einstein to his greatest insight. Einstein took seriously the idea that gravity might not be a force at all. In curved space-time, objects move along the straightest possible paths, called geodesics. From within that curved geometry, motion looks accelerated, but from the standpoint of space-time itself, nothing unusual is happening. Standing on Earth, you are not stationary. You are accelerating upward, pushed off your natural falling path by the ground. Astronauts float not because gravity is absent, but because nothing prevents them from following it. Einstein's equations, brutal and complex, describe how energy and mass shape space and time, yet they reduce to Newton's laws when conditions are gentle. This is not elegance for its own sake, it is survival. Nature allows simple descriptions when deeper structure is unnecessary. Still, Feynman remained uneasy. Acceptance did not mean satisfaction. The equations worked, predictions matched reality, but something fundamental was still missing. Gravity refused to fit alongside quantum mechanics, and that refusal mattered more than any conceptual comfort. The weakest ruler of all gravity's strangest feature is its weakness. Compared to electromagnetism, gravitational attraction between particles is smaller by a factor of about 10 to the power of 38. At atomic scales, gravity is irrelevant. Electromagnetism builds matter, binds atoms, and creates chemistry. Gravity only matters when mass accumulates in astronomical quantities. Its power comes from a single uncompromising trait: it never cancels. Electric charges balance out, but every bit of mass adds to gravity's pull. What gravity lacks in strength, it makes up for in patience. Gravity also does something no other force does. It reshapes time itself. Clocks run slower in stronger gravitational fields, a fact that must be corrected for in everyday technologies like satellite navigation. Light, despite having no mass, bends in gravity's presence because it follows the geometry of space-time. Black holes reveal the extreme edge of this behavior, where space-time curvature becomes so intense that our equations collapse. As Feynman bluntly observed, when equations explode, it is not nature that has failed, but our understanding. The greatest unsolved problem remains gravity's refusal to coexist peacefully with quantum mechanics. The other forces can be described by exchange particles. Gravity resists this treatment. Feynman tried to quantize gravity and failed, admitting that failure openly. He suspected that gravity might not be fundamental at all, that it could emerge from deeper principles, just as temperature emerges from molecular motion. This was not a claim, only an honest possibility. The final misunderstanding about gravity is believing that science has already finished the story. For Feynman, science did not provide comforting answers, it refined uncomfortable questions. Gravity works flawlessly, predicts accurately, and governs the universe, yet what it truly is remains incomplete. Gravity does not pull the universe together, it tells the universe how to move. Its deepest lesson is not certainty, but humility, a reminder that the most reliable laws can still hide the greatest mysteries.